Hey everybody, in this video we'll talk about writing solutions to a 3x3 system given a augmented matrix. But first let's talk about what different type of solutions we might see and why they look that way on matrices. So if you recall, when we were solving systems of equations, or our previous videos on this, that we learned a system may have no solution. It could have one solution or it could have infinitely many solutions. But if it has no solution, the system is said to be inconsistent. Okay. We must recognize that an inconsistent system occurs in a matrix if the matrix reduces to a contradiction. Look at this third row. As we get to the point where we're doing row echelon form or reduced row echelon form, we end up getting all of our variables, or 0 times all of our variables, which is 0, is going to equal 2, that's never a true statement. That's never going to happen. So when that happens, we say that the system is inconsistent and there's no solution. Okay. For the next instance, when we're working with two variables, okay, we can have the solution to the system of two variables, or two linear equations, is a point at the intersection of a line like this. If the two lines are parallel, then we have no solution. If the equation of the system represents the same line, so it lands on the same line, we say the equations are dependent, and the solution set is all the set of points on that line. So here, when we do reduced row echelon form, or we try and get to that, we end up getting 0 equals 0 on the bottom, which is true. And that means that one of these equations was the same as another one. Right? So we're going to have infinitely many solutions, independent equations. Now let's look at some examples. Here's our first example. What do we get here? We get on the bottom, on that denominator, the third row, that 0 equals 0. Right? We also have that 1x minus 5y equals 3, and that z equals 3. And we have the 0 equals 0 bit as well. What can I do with this information? Well, I could put everything kind of in terms of y, because from here I can say, well, x equals 3 plus 5y, z is going to equal 3, which is kind of in terms of y. There's no y's there. And then y is just going to equal y. So we're going to have infinitely many solutions where y equals y, and x is 3 plus 5y. So that's what we would put into this box here. And then we would have y, and then in that third box we would have 3 for z. So that's one example of an infinitely many solutions problem. So let's look at this augmented matrix and come up with our equations that we would have from this. We would get 1x equals negative 2, 1y equals 1, and then we would have z equals 3. So for this problem, we have a unique solution at one point, and that is x, y, z, or negative 2, 1, and 3. And there's our solution. Okay, let's keep going. For this one, the first row means that x equals negative 7, The second row says that z equals -4, and the third row says that 0 equals -4. That's false. So when we get a contradiction or a false statement, we say there is no solution. Okay, let's look at this one. This one says that x plus z equals -2. And it says that y plus 2z equals 8. And then it says that 0 equals 0. So the 0 equals 0 signifies, hey, we're going to have infinitely many solutions. But then how do we put that in some kind of form that we understand? Well, I can see that if I put x in terms of z, x equals -2 minus z, y equals 8 minus 2z, and then z in terms of z is just z. So for these problems we have to think, can I put all of my variables in terms of another variable? The problem a few times ago, we could put things in terms of y, right? But this one, we can put things in terms of x, or z. So we use this form where x is -2 minus z, y is 8 minus 2z, and z is just going to be equal to z. Okay, so there's another example of infinitely many solutions.